All right, it's 8:30. Let's go get started. All right, morning, everybody. What do you do today? All right. So, of course, first thing probably everyone noticed, and probably already seen your grades. So I've finished grading the midterms as of yesterday afternoon. It was a little bit rough, I have to admit, it was definitely kind of a rough exam. I think looking back at some of the work that I did, at some of the solutions that for the exam, they were a little bit harder than I thought. And so that's why kind of the average kind of came out a little bit lower than expected, but that's okay. We'll kind of learn from this and we'll move forward. And so with that in mind, I did want to do basically like a mid-semester check-in survey. So it's not up on Canvas yet. So I was going to post it today. And so basically, I want to kind of just survey you guys, see how you guys are doing in the class. See what's working, what's effective for you guys, and what are things that I can do better to make sure that you guys succeed in the course. Okay. And so it's about 5 questions. 4 of them are multiple choice. And so it's just, how are you feeling in the class and things like that. So I don't think it's going to take you more than 5 minutes to do. So that's going to be due next Sunday. So basically the same due date as homework 4. And I do want to give you guys points for it. So, I don't want to just survey you guys and give you nothing for it. And so it'll be worth about 40 homework points. Okay. And the responses are totally anonymous. And so I don't know, who's saying what, unless you put your name in the free response, then I won't know. And so, it's really important for me that you guys be honest with, how this class is going. Okay. So, really give me your honest feedback. If the class is going terribly for you, I want you guys to tell me. If I'm doing like, a shit job, I want you guys to tell me. Because, we're about half, we're basically right at the halfway point of the semester now. And, for the second half of the course, I want to make sure that I'm doing everything I can to make sure everyone succeeds in the course, right? So, of course, I have my own perception of how things are going with the course, but, it's interesting. I feel like I'm kind of reaching that point in my career where, like, when I first started, I felt like I had a good handle of, how things were going in the course because I was just a student, not too long ago. But now that this is my 5th year, I feel like I'm kind of losing that a little bit. So, I've been kind of an instructor too. I've been on this side of I've been on this side of the podium a little bit too long. So, I really would like you guys to tell me, how, be honest, how things are going in the class. Tell me what I can do better as an instructor, just so, we can make the second half. We can really finish this class strong. Okay. All right, so that's going to be up after the class. I'm going to send an announcement as well, just to kind of remind you guys to do it. So please fill it out. It's basically free homework points, and so it's not extra credit. So it does count as kind of like an extra assignment, but an extra 40 points on your homework can do nothing but help. Okay. All right, and so with that, so I do have the exams today. So I know probably most of you in class here are looking forward to picking them up. So I'll give those back out at the end of class, so you can look at it. I did try to leave as many comments as I could. I gave you guys a lot of feedback, so definitely take a look at that. I'll be posting the midterm solutions as well, just because a lot of this stuff is going to come back for the final exam, and so I want to make sure that you guys kind of can kind of learn from this midterm, and then kind of apply those things towards the final. Okay. All right. And so with that, the plan for today is we're moving on to the next section of the of vector calculus, and so today we're going to go over integral stuff. So we're going to go over line integrals and Green's theorem. So that's the plan for today. All right. So I said this on Tuesday too, but I think it kind of bears repeating today. A little bit about my grading policy. So I don't curve individual exams. So I kind of just leave the exams as they are. But then what I do is I wait until the end of the semester. So once all the grades are in, midterms, both midterms, homework grades, final exam grades, and I see where the course average is. And if that course average is below, a certain threshold for this class, I think the threshold for this is around like 75, 77%. And so let's say the class average ends up being like 70% by the end of the course. And so what I'll do is I'll add, 5, 6, 7 points to everyone's grade until the overall average of the course is at that. So, I think, in my opinion, I think this is kind of the simplest and kind of most straightforward way to kind of scale the grades up to that time. So this exam for you, I'm not going to curve it. I'm going to wait until the end. Okay? And I'll be transparent about that too. So once everything's in, I'll send an announcement to the course that the class average is this. I'm going to add X amount of points to everyone's grade. So whatever grade that you see on Canvas, just add X amount of points, and then that's going to be your final. Okay, any questions on anything before we get started for today? Okay, all right, so let's go ahead and get started. And so the topic for today is the vector integral. Okay. So on Tuesday, we just finished talking about differential calculus. And so there were three main operators that we went over. So one was the gradient. Two was the divergence. Three was the curve. So those are the three main operators that we went over on Tuesday. Okay. And so they all have their own ways to compute them. And so we reviewed that. But I think more importantly, we talked about kind of what, how to actually interpret these operators. Okay. Because when you kind of connect these operators to, especially applied engineering, they all have kind of a unique kind of physical interpretation. Okay. And so that's kind of the focus I want you guys to think about, from last week and this week, especially today, is, we have these mathematical operations, you've probably seen them before in maybe a previous math class, right? So, I don't want to focus so much on how to compute these, but I want you guys to focus on, when you see these kinds of operators in an equation or when in another engineering class, I want you to have kind of a good physical intuition for what that actually means in an equation. Okay, because ultimately, as you get into more and more advanced engineering, the equations get more and more advanced, right? And so once you kind of get past a certain point, and probably for most of you guys are past this point already, the equations get so complex that you can't actually solve them. So you think of equations like Navier-Stokes equations in fluid mechanics. You think of equations like even the heat equation in heat transfer, right? You don't actually solve these equations, at least not in the general sense. And so what's more important is that you kind of look at these equations and you kind of look at all the terms and you look at kind of the structure of the equation itself, and you can kind of, interpret behavior from that equation, right? And so that was kind of the point I wanted to make on Tuesday. Okay? So today we're going to do the same thing, except with integral operations. The first what we're going to do is we're going to talk about the concept of a line integral. What that is, how to compute it, and how to more importantly interpret it. And then the other point we're going to make today is one of the more important theorems in applied mathematics. That's Green's. Okay. So that's the plan for today. And I will say that, even though, we're talking about this now, I've had similar kind of lectures. I've had similar kind of, discussions, when I was an undergrad too. But, for a lot of these things, these didn't really click for me until I reached graduate school, or until, even when I'm teaching. So, and so, the way I'm going to teach this is, it's part of it's going to be traditional, but part of it is also going to be kind of my own kind of interpretation of this, what kind of took me years to kind of really understand. And so what I'm hoping is that, that is going to help to kind of better understand why these mathematical operations exist and, what their purpose is. Okay. And so these in particular are useful for a lot of applied engineering. You've probably seen a lot of these already if you've taken fluid mechanics, and so these are used in a lot of conservation laws. Particularly things like Reynolds transport theorem or any kind of integral conservation laws. So that's mass, momentum, and energy. I think I think electromagnetism uses quite a lot of these as well. But that is very outside my area of expertise. So I can only go off my vague memories of Okay, all right, so let's start with line integrals. But before we talk about line integrals, we have to talk about parameterized curves. So what the heck does that even mean? Because in order to compute a line integral is basically a one-dimensional integral that goes through space. So before we can actually do that, you have to take a curve and parameterize. Okay, so a parameterized curve is a path in space Okay. This could be either 2D or 3D space, as long as it's not 1D space, because 1D space is just a line. Okay. Where each component of the vector path depends on the same parameter. And so it looks something like this. And so usually we use the symbol R, and we give it the little vector symbol on top. So we say R vector of T. Okay. T there, that's our parameter. So that's our single parameter of our curve. In three-dimensional space, this is going to be X of T, Y of T, and Z of T. So you can see here, we have a traditional kind of coordinate or a traditional vector that represents your position on the path, and each of those depend on the same parameter T. Okay. X, Y, T, X, Y, Z denote position. And so the reason we call it a path, or the reason we call it a parameterized curve, is that you can literally kind of imagine yourself walking along that curve, right? And so a lot of times, we have something like this. And so let's say that we have, typical coordinate system. So let's say we have X, Y, Z, okay? And we have, a curve in space. And so in the blue right there, that is our curve. So that's the path that we're parameterizing on. Okay? And then depending on your position on the path, we can characterize it using the arrows. Let me go ahead and draw three positions here. So this position here, we might be at T is equal to T1. Okay, so that's the first position. So when T is equal to T1, we plug that into X, Y, and Z, and then we end up with that position there. Right, second position, we move T to a second value, so T is equal to T2. So then we move on to that position of the curve there. And then finally, we might move on to a third position of the curve. So we say T is equal to T0. Okay, so we're literally kind of walking along the curve. So as t, usually t starts from 0 and then we increase it up to a certain value. As we increase the value of t, we kind of literally walk along this curve. And so that's why we use the symbol t, because for some people they interpret t as literally time. And so as time passes and we walk along the curve, we're on different positions on that curve. So t is our time variable, and the function x, y, and z, that those determine how our position changes with time. Okay. And so basically we're taking a three-dimensional object or three-dimensional concept of position, and then we're kind of having it all depend on the same parameter. Okay, so that's what a parameterized curve is. Okay. Any questions on this here? Okay, so let's do an example, very simple one. So let's look at a circle. So a circle looks like this. Good old circle. And so if we were to write the equation for the circle in x, y, it would look like this: x squared y squared equal to r squared, where r is the radius of the circle. Okay. Just for the sake of this example, let's pretend, let's say that we have a radius of 2. And so instead of r squared there, I'm going to say this is b. Okay. Okay. So that's our xy equation for a circle. Right? If we were to parameterize this, and so let's say that we wanted to parameterize it in the way that we walk around the circle, we take a path around the circle, we would look like this. We have r of t is equal to 2 cosine t, comma 2 sine t, and then I'll put z there just because even though this is a two-dimensional problem, we should still put z there as well. Okay. And so our parameterized curve here is 2 cosine t, 2 sine t, and 0. Okay. So of course, our 2 cosine t here that's x of t, our 2 sine t is y of t, and our 0 is z of t. Okay. The first thing I want to do is just to kind of prove to you that this parameterization satisfies our original equation. Okay. And so let's go ahead and plug it in. Let's verify. Plug in. Okay. And so we plug into our original equation here. We have x squared. So x squared is going to be 2 cosine of t squared. Okay. Plus y squared, so that's 2 sine of t squared. And if this is going to satisfy this, then it should equal to 4. Okay. So let's check and see. So first thing I'm going to do is I'm going to take 2 squared and factor that out for each term. Okay. Okay. So you have 2 squared times quantity cosine squared of t plus sine squared of t. Okay. And ideally, this should equal to 4. Right, so we have cosine squared plus sine squared, so that is one of the trig identities. And so this entire quantity here is equal to 1 via trig identity. And so if that whole quantity is equal to 1, I'm going to go ahead and square 2. So we have 4 times 1 equal to 4. And so that is true, right? So 4 times 1 is equal to 4. So, this is verified. So our RT follows the path of a circle. Okay. Any questions on that so far? Okay, so now let's interpret this curve and let's see how we actually use it. Okay. So our RT T 2 sine T and 0. So let's plug in various values of T here, and then let's see kind of where we are on the curve. So let's plug in T is equal to 0. Guess we're going to plug in R of 0. So R of 0 here, we're going to have 2 cosine of 0, 2 sine of 0, and 0. Okay. And so we compute those trig functions there. And so 2 cosine 0, cosine of 0 is just 1, so we end up with 2. Okay. Then we have 2 sine 0, sine 0 is just 0, and 0 is 0. And so let's plot that on our xy plane. So, if we plot that out, we are on the x-axis, right? So we're at the coordinates 2, 0, 0. So this is our location at t is equal to 0, right? All right. Let's try another coordinate. So let's try t is equal to pi over. Okay. So r pi over 4, 2 cosine pi over 4, 2 sine 4, and 0. Right, cosine pi over 4 and sine pi over 4 are the same thing, and so they're going to be root 2 over 2. And so this gives us root 2, and 0. And so root 2 over 2, that is about right here. And so this is at t is equal to pi over 4. Okay. And so now that we have 2 points along the curve, we can start to see its path, right? So when we start at t is equal to 0, then once t advances to pi over 4, we kind of advance up there. So we're basically walking counterclockwise around the circle. Okay? We're going from here up to there. Okay. Okay, we'll do one more. So let's do pi over 2. R pi over 2 is equal to 2 cosine pi over 2, 2 sine pi over 2, and 0. Okay. We plug in for those values. Cosine pi over 2 is just 0. Sine of pi over 2 is 1. We have 1 times 2 is 2, and 0. Okay. So now we're on the y-axis, and so one right here. T is equal to pi over 2. And so again, we progress kind of more counterclockwise around the circle. Okay. All right. So that's I think the important point to remember about these parameterized curves is that not only do they draw a shape in space or they draw a line in space, but you're literally traveling along that line, right? So for different values of t, you're going to be at different points on the line. Okay. And so of course we can continue this, and so if we do 3 pi over 4 pi, 4 pi over 3, 3 pi over 2, and 5 pi, 7 pi over 4, we eventually would make our way around the circle completely. Okay. All right, any questions on that? Okay. All right, so now that we kind of understand the concept of a parameterized curve, let's talk about the tangent. Okay, so if the parameterized curve that defines kind of our path in space, we also want to compute its tangent, or basically a line that basically just touches or is parallel to the curve at a particular point. In other words, that you can interpret this as the slope. And so the way that we compute this is we keep r to t. And we're just going to take the derivatives of each of the components. We have the x dt, the y dt, and dz. It's very straightforward. So we just take the derivatives of each of these components. All right. So you can take our previous example, and you're going to take the derivatives of cosine and sine, and that gives you the tangents of the curve. Okay. So there's not much more I want to say about that. It's going to show up in Green's theorem and stuff. So I want to make sure that when you see this, because it looks a little bit weird, and even to this day, it looks a bit weird to me when you're taking the derivative of a vector with respect to something. But that's basically how we're interpreting this. We're taking the derivative of each component of that vector by the same variable. Okay, so now that we've gone over paths, we've gone over tangents, we're ready to talk about line integrals. All right, so a line integral, I think kind of the easiest way to interpret it is that it's almost like a generalization of a typical 1D integral. Okay. And so if you think of a 1D integral, a 1D integral looks something like this. F integral f of x from a to b dx, right? And so visually what this looks like is that if we draw an xy axis here, okay, and we have the points A and B on x, right? So we have a function that's a function of x, and and we can draw those locations. Okay. The 1D integral is basically integrating along this path, or the function. It's integrating the function along the path from A to B, but our path is just a flat kind of horizontal line. So that's good when our function is a function of x, but sometimes we want to integrate a function that's arbitrary in space. Okay, so our path is not only just, we want to generalize, so our path is not just a horizontal line, we can do parameterized curves as well. Okay. Okay, so the result of that is the line. So mathematically it looks like this. So we look at the integral. Okay. And instead of integration bounds, I like to put like a subscript c. And so what that subscript c there, what that represents, that we're integrating over a curve. And so usually what we have here is that we're integrating some function f. Okay. And that function f here is going to be a vector field. Okay. F is a vector field. But we're going to parameterize that vector field according to our parameterized path. So mathematically looks like this. And then we're going to take the dot product with that, with the tangent. All right, so that's kind of the shorthand. That's kind of the lazy person's way of writing this. But when you write it like that, it seems a little bit opaque. It kind of seems like I have no idea how to compute this. It's just a bunch of math symbols together. Okay, and so put this in terms of expressions that we've seen, at least today, it would look like this. So f that's parameterized by r of t, dot product with the tangent of the curve, so dot product with dr dt, and we're actually integrating over dt. Okay? And we're integrating over from two different values of t. So we're going to start at t is equal to a, and then t is equal to. This right here, I think, is a little bit more useful form for the line. And we'll do an example soon of what that looks like. And in fact, actually, you can expand this kind of one more time if you wanted to kind of get rid of this dot product here. And so if we expand it one more time, and so we're going to assume that the vector field has components f1, f2, f3. Remember, a vector field is basically a multi-valued function. Okay? So we have three components of the vector field here. And so if we expand that, and then we take the dot product with the tangent, and so we have our formula for the tangent up here, then our line integral would look like the following. So integral a to b, and remember these are values of t, f1 of t times dx dt plus f2 of t y dt plus f3 of t dz dt. Actually, probably this one is the most useful form, because then you can kind of take your components of the vector field, multiply them by the components of the tangent, add them all up, and then you just have just a regular integral form. Okay, so let's do an example to kind of see how this is. So let's compute the line integral of the vector field. we have f is equal to z, x, and y. Okay. And we want to do this along a helical curve. So r of t is equal to cosine of t, sine of t, and 3t. Okay. And we want to do this for t goes from 0 to 2 pi. Okay, so we have our vector field. Our vector field, very simple in this case, is just z, x, y. We have our path, okay, and we want to integrate or do a line integral of that vector field along that path. Okay, so visually it kind of looks like this. And so if we draw, x, y, z. But whenever you draw things in 3 dimensions, it's always tough, especially for people like me who are artistically challenged. Okay. And so our helical path looks like this. And so when t is equal to 0, we start at a location 2, 0, 0. Okay, so we just plug in t is equal to 0 into RT. Okay. So this is our starting point. Okay. And then as t increases, because of the cosine and sine, we're going to start rotating around the z-axis. But if you notice here, our path here has a 3t for the z. Okay? So we're gradually going to be moving upwards while kind of rotating around. So it almost looks like a coil. So you can think of it as there's a cylinder of radius 1 in this case, and we're kind of wrapping around that cylinder as we go up. Okay. So from 0 to 2 pi, our path would look something like this. Of course, that's a terrible drawing. I have to make comment about my terrible art every time I draw something, because my wife is a graphic designer, and so she spares no opportunity to tell me how terribly I draw. It's funny because she'll always ask me, she'll like design something, like an ad or something. Oh, how does this look? And I'll say something, and she's like, "That's a terrible opinion. Why would you say that?" It's like you asked my opinion, right? That's your fault for asking for my terrible artistic sense. Okay, so let's go ahead and start doing this problem. Okay? All right, so our line integral that we want to plug in for is essentially up here, right? But before we can do that, our first step is we need to basically parameterize our vector field according to our path. Okay? So we have f is equal to z, x, and y. And so first thing we're going to do is we're going to plug in our expressions for r of t, right? So r of t, remember that's functions x of t, y of t, and z of t. Okay. So let's go ahead and plug that into this expression here. So first we have z, and so according to our path here, our z is 3t. Okay. Then we have x, and so our x here is cosine of t. And then our y here is sine of t. So let's go ahead and plug them. And so these are the components of our vector field. So this is F1 of T. Over here, so it stands out. F1 of T, F2 of T, F3 of. Okay, that's good. Step 2, we're going to compute the tangent of this curve. Or this path. Okay. Okay, so we have dr dt. Okay. So I'm going to take our path here, r of t. Okay. I'm going to take the derivative of each component. So first we have derivative of cosine t. Let me write it down. d dt cosine t d dt sine t and d dt. All right, we're just taking each component of our path and we're taking its derivative. All right, so first we have derivative of cosine t. Derivative of cosine t is just minus sine t. So we have minus sine t. We have derivative of sine t. Derivative of sine t is just cosine t. And then we have derivative of 3t, which is just okay. So now that we have the tangent of the curve, we're going to compute the dot product. And so the dot product here is going to be f r t, dot product with the tangent. And so if we write that out, we have 3t on cosine t, sine t, dot product with our derivatives, minus sine t, cosine t. We're taking the dot product of basically, we did step 1, step 2, we're just taking the dot product of step 1 and 2. Okay. And so if we do that, we have a minus 3t sine t, okay, plus cosine squared of t plus 3 sine t. Okay. And then we're going to integrate this from 0 to 2 pi, because those are the bounds on t. Okay. So we end up with this integral right here. So this is not a nice integral to do. It's doable. You can definitely do it. But it's not going to be fun. So what I'm going to do, I'm not going to go through the details of integrating this, but I will tell you kind of the strategy that I would use for each term here. Okay. And so because there's a plus sign between each one, we can integrate each of these terms individually, right? So we have the 3t sine t, so I would integrate this by parts. Okay. The cosine squared of t, first thing I would do is I would use the double angle identity. And then the 3 sine t, that's probably the easiest term that we have there. We can just integrate that straight up. And so if you do each of those integrals, you you actually do them out. And what you get is, so the integral of this first term right here ends up being 6 pi. The integral of the second term of cosine squared of t, that ends up being pi. And the integral of sine, so this is probably the easiest one to verify. You integrate sine, you end up with a minus cosine. And so you integrate minus cosine from 0 to 2 pi, that just ends up being a full circle. And so you end up with 0. Okay. And so we add these up together. Our total line integral here is 7. Right, and so that's all there is to a line integral. So a line integral is like, it's like a regular integral just with extra steps to set it up, right? So you do a couple extra things, you take your vector field, you parameterize it, you take the tangent of your curve, you dot product it, and then from there it's just a regular integral. And so you kind of carry it out. That's normal. All right, any questions on this example here? Okay. All right, so a couple extra things before we move on to Green's theorem. And so the path that we just did, we did a helix, right? And so kind of the unique thing about line integrals is that the value that you get from the line integral not only depends on the vector field. And so our vector field is f. And so you can almost think of f as like the function that we're integrating. Okay. And so of course, it's going to depend on that. So you integrate two different functions, you end up with different integrals, right? Right. So that's true even in traditional integrals. Okay. It not only depends on the function, but it also depends on the path that we take through that vector field. And so we can have the exact same function. But if we take two paths, most of the time, we're gonna end up with two different line integrals. Okay. And so let's use the example that we did last time, right? So for the example we did last time, we go again, part, my favorite thing, right? And so for the example last time, we took this kind of helical path. So we started here and we kind of rotated around. Okay. Okay. If we did a completely different path, and so let's say that we took a path from the origin, and then we walked just straight up the z-axis. Okay. So the green path here, we walk straight up the z-axis. Okay. Even for the same vector field, right? So even for the same function f, that z, x, y that we had, for the purple path and the green path, we're going to end up with different line integral values. Okay. And so this idea that we get different integral values for different paths is this idea called path dependence. Right, so all that means is that when you compute a line integral through this vector field, then you get different values depending on the path. Okay, and this is a property of the field itself, and so there are certain fields where it's the path that you take is different. Okay? The opposite of this is of course path independence, and so that might have been a term that you may have heard in a physics class. And so for path independence, it doesn't matter what path that we take through the vector field. We're going to end up with the same value as long as the starting point and ending point are the same. And so regardless of the path that you take, as long as you start at the same point for a path independent field, you're going to end up with the same line integral value. Okay. And so you can take a direct path. And so if you go from point A to point B, you can take a direct path, you get a line integral in one way. Or another way, you can walk all the way around the world and then end up at the same path. You're going to end up with the same line integral value. Right, so sometimes what you'll see, the terminology that's used for this, I know in fluid mechanics we use this term. I don't know if it's used a lot in heat transfer, but sometimes you'll see these called potential fields. Okay. So the most classical example of this, of a path independent field, is gravity. So gravity is all around us. It's pulling us towards the core of the Earth. Okay. And so if you compute the work that gravity has done, it doesn't really matter what path that you take through the gravity field. All of that matters is essentially just the change in height. Okay. Okay. And so if we look at an example here, so let's say this is the ground. And you take a ball and you drop it. Okay. Right, and so if you take an object from a high height and you let it drop, gravity is going to do work on that object to pull it down towards the Earth. Okay. You can take that same object and then put it on like a slide, like a chutes and ladders type of thing. Okay. And so, of course, the ball is going to follow this path. Okay. And so in both instances, even though in the second instance, in green here, the ball is traveling more distance, right? Because it's sliding along the path. Gravity is going to do the same amount of work because it's the only thing that matters is just the starting point and the ending point, which is be dropped from the same height. Okay. Any questions on path dependence, path independence? Okay, One last notational thing before we jump into Green's theorem is sometimes you'll see a line integral with like a little circle. Okay? And so sometimes you'll see a line integral that looks like this. Okay? And so when you see an integral sign with a little circle like that, all this basically means that we're taking a line integral around a closed path. Okay, so the starting point and ending point are the same. Okay. So that's all that means. All right, so of course, if you take a line integral on a closed path or a path independent field, you always get 0 because the starting point and ending point are the same. It doesn't matter what path that you take, as long as you start and end at the same point, you end up with. Okay, so now that we've done line integrals, let's go ahead and move on to Green's theorem. And just to keep things simple for this class, we're going to limit ourselves to just a plane. Okay, so we're not going to go outside. Okay. So Green's theorem is the first of the integral theorems that we'll cover. Okay. So there's 3 that we're going to cover. So we're going to cover Green's theorem, we're going to cover divergence theorem, and Stokes theorem. Okay. And so all these kind of integral theorems have kind of one thing in common. So they involve basically the transformation of one type of integral to another. Okay. And so all of these theorems kind of have the same form. So you have one type of integral on one side of the equal sign, the integrand is something, and on the other side of the integrand, there's, on the other side of the equal sign, there is a different type of integral with a slightly different integral. Okay, but they usually involve usually the same vector field, and usually one is like on one side is going to be either a line integral or surface integral, and on the other side is going to be like a traditional double or triple. Okay. And so, of course, the way that this is used traditionally is to simplify some expressions. And so if you look at a lot of physical laws, they're given in terms of, line integrals and surface integrals. Normally, those are a little bit more difficult to compute. And so these theorems are used to kind of convert those into a form that's a little bit easier to compute. Okay. But I think, what's more important in these theories is, like I mentioned at the beginning of class today, is that they all have kind of a physical interpretation, or there's a physical meaning behind these, or there's a physical analogy that you can put behind these. All right, so let's start with Green's theorem. So Green's theorem is a transformation of a double integral and a line integral. A double integral to a line integral and vice versa, of course, too. And so visually it looks like this. And so, in a plane, and we're just concerning ourselves with two-dimensional objects now. So let's say we have an arbitrary blob of something, okay? And so that is our region, okay? We'll call this the region R. So we have a closed region R. And more importantly, for this closed region R, we also have its boundary curve, right? So there's a line that goes around, more importantly, a closed line that goes around this region. And so I'll call that curve C. Okay. And so C goes around R. Okay. So this is kind of an important point in Green's theorem, is the fact that even though we're transforming between a double integral, of course, a double integral is taken over a two-dimensional space. Okay, so it's a double integral, and we're going to be transforming that into a line integral. Okay, it's important to know that these two are connected, and so it's not just a random 2D integral, and it's not just a random line integral. Okay, the line integral actually goes around our region. Okay, so they're from the same geometry, except for one case you're looking at the actual area, the other case you're just looking at the path around the area. Okay. So another thing to note is that inside this region, we're going to have a vector field. And so we have F vector field is equal to F1. F1 is going to be a function of X and Y, and F2 is also a function of X. Okay. Okay. And so with all this in mind, so now that we have kind of done all the setup, let's go ahead and state Green's theorem. So I'm not gonna prove it. We don't really have time to prove all of these integral theorems. But let me just show you the final form. This is Green's theorem. How appropriate that we're covering Green's theorem the day before St. Patrick's Day. Okay. Green's theorem is, on one side of the equal sign, we're going to have a double integral. And this is going to be around the region R, okay, or through the region R, I would say. Okay. Then on this side, we're going to have the curl of the vector field. So we have partial F2, partial X minus partial F1, partial Y, dx dy. Okay. And this is equal to a line integral around the curve C. Okay. And the fact that it's a closed integral, I'm going to put circle around this this curve, okay? Because we're making an entire map around the region R. Okay, so our starting and ending point are the same. And this is going to be F1 dx plus F2 d. This side of the equal sign, we have a double integral over the 2D region R. And on this side, we have a line integral around the curve C that goes around. Okay. All right, so that it's kind of variable form. Another popular form for Green's theorem utilizes our vector calculus operators from Tuesday. Okay. And so another form for this is double integral of R. We have the curl of the vector field. Okay, so that's nabla cross F. Dot product with K hat. Dx dy. Do. Around C. F. Of R of T. Dot product with dr. Right. So the top and bottom are the same. It's the same theorem, just put in slightly different forms to make it. Okay. Right. So we have about 7 minutes left, or I guess a little bit less than 7 minutes. And so I have a couple of things for Green's theorem. So I have an example that shows you how to actually compute it, and we'll actually verify that this is true. And I have the physical interpretation. Okay. I do want to spend a bit more time on the physical interpretation, but I know this is probably the worst time in the semester to do that, because I know everyone's a little bit antsy to get to their exams. And anything that I say in the next 5 minutes probably be forgotten. Okay. So what I'm going to do instead is I'm going to give you just a preview of the physical intuition, and then when we come back on Tuesday, we'll kind of expand on it in detail. Okay. All right. So the physical intuition of Green's theorem, has to do with this idea of circulation. Okay. And so if you remember at the end of lecture on Tuesday, we talked about the curl and what that means for rotationality or irrotationality. Okay. And so the fact that we see the curl here kind of gives us an indication that Green's theorem has something to do with rotation as well. Okay. And so the physical interpretation of Green's theorem is basically when you have your vector field F, a lot of times you're interested in how much the field itself is rotating. Okay. And so the physical interpretation is that there are multiple ways to basically quantify or to basically compute how much a vector field has spinning tendencies. Okay. For example, we have two-dimensional vector field. And so just based on the path of the arrows that I'm drawing here, you can kind of see that the vector field is kind of swirling a little bit. And so we're kind of doing like, use a different. Right. And so you can see that, we're starting to kind of rotate kind of upwards, okay? And so this has a lot of applications, especially in fluid mechanics. And so especially if you get into things like aerodynamics, and you're designing, flow over airfoil, right? A lot of times you're interested in a quantity called vorticity. Because when fluids spin, okay, so when they have these kind of little vortexes in space, that leads to a lot of very interesting properties, especially when you're talking about, aerodynamics, where you're concerned about lift and drag and things like that. So the amount of spinning or the amount of rotation or circulation, we'll cover that term on next Tuesday. It has a big effect on the physics of your system. Okay, and so Green's theorem is something that's used quite a lot in aerodynamics to kind of transform integrals that all involve kind of vorticity and spinning. Okay. All right, and then we'll leave the rest of it for Tuesday. All right, any final questions before we wrap it up for today? Okay, all right, so I have your exams here, so you guys can come up and get them. Thanks. With the two files here. So for the people that weren't able to staple their cheat sheets, they unfortunately came out, and so I kind of left them on the side right here. And so they're in here somewhere. Or maybe I left them in my office, but if they're not here, I'll bring it on. All right, so thank you guys for coming today. Hope you guys enjoy your weekend. Remember to do the mid-semester check-in survey, so I'll post that as soon as I get back to my office. And I'll see you guys next week. I look forward to I think Yeah, I think I might have left in my office. I'll bring one. Yeah.
Order.
Any final questions? I'll bring the exams back on Tuesday, so if you're not able to make it today. Okay, all right, no more questions. I'm gonna go ahead and close the call. So have a good weekend. I'll see you next.